Okay, welcome everybody. This is the lecture course on black holes. My name is Volker Perlick. This course is meant for three groups of people. The first group is master students here in Bremen. I think that's the majority of the people here in the room. I'm very happy that the number is much higher actually than I expected. Let's see how many of you will survive until the end of the course. So that's the first group, and they can take this this course towards their master degree if they do this module which is called astrophysics. In this module, it is worth 6 credit points. So if you combine it with some other courses, so that you get 15 credit points altogether, then you can do an exam in this module, and this counts towards your master degree. So that's the first group. The second group is PhD students in our research training group, Graduiertenkolleg in Germany. In German, that's a group of PhD students who are partly here in Bremen, partly in Oldenburg, partly in Bielefeld. And because it would be difficult for the people in Oldenburg and in Bielefeld to shuttle back and forth twice a week between their hometown and Bremen, we decided to record the lecture. So everybody has a chance to watch the recordings afterwards. And there's a second consequence of the fact that we want to make it for the PhD students available. I have to do the course in English. Otherwise, here in Bremen, of course, I would teach in German, but because actually the majority of the students in the research training group comes from abroad and doesn't speak, at least not perfectly, German. So that's the reason why we have to do it in English. But the audience here in the room should feel free to ask questions in German. That would be perfectly all right. I have to repeat questions anyway over the microphone so that everybody understands what the question is, and I can then answer them. Yeah, for the people who watch the recordings, there's of course no chance to ask questions during the lectures because they can only watch it afterwards. But I'm happy to answer questions by email. So if everybody who is watching the course or who is here in the audience and sometime later a question arises, then of course feel free to send me an email. And if it's something of interest for everybody, then I would discuss it later. So here I have the times for the lectures. That's just for those of you who want to attend the lectures physically here in Bremen in the room. So we have 2 hours, which means 1.5 hours actually, lectures on Tuesday. And we have 45 minutes lecture on Friday and 45 minutes tutorial on Friday. And we will record only the lectures, so the tutorials will not be recorded. So we will do the tutorials in the way that, at least I hope that it will work in this way, that some students come to the front and present the solutions on the board. Actually, last term, my GR course worked very well. Actually, I think I didn't have to present the solution for any problem myself. Every time one of the students did it. So I hope it will work the same way. But I think it would inhibit maybe the students a little bit if we would record this. So I think we do not record the tutorials. So I should write down, first of all, the course, as we do it in English, it's now called not Schwarze Löcher, but rather black holes. I would write my email here for all those of you who want to ask me questions or have comments or whatever. So that is Perlick at zarm, zarm, .bremen, de. And what else did I want to write? There was just something I said. I'm sorry?
Are you sure? It is Uni minus.
Ah, sorry. You're right, of course. Thank you. So it's Uni minus Bremen.de. Yes. And what else did I wanted to say? Yes, we have the times, and oh yes, now I know what I wanted to say. I will send, so you will not only have the possibility to watch the lectures, You will also get written lecture notes, and I will distribute them once a week, I guess around Monday each week. So this will be the material from the last week in written form, and I will also send the worksheets, and 1 week later the solutions to the worksheets. And this will be sent to everybody who has registered at StudIP, and to anybody else who is interested. And if you have not registered via StudIP but want to receive this, then please just send me an email. Then I will put you on the mailing list, and you will. Those who are registered via StudIP will get it automatically, but the other ones should send me an email. So that's the way in which the course will run. Okay, I think that's all on the organizational side. If there are no questions on the organizations, then I can tell you, well, first of all, I should say a few things about literature. So as I said, I will distribute written lecture notes, but nonetheless, I think it's always a good idea also to read about the matter from some other sources. So I will mention a few textbooks which treat black holes, and also a few monographs. And yeah, I would encourage you just to read in parallel a little bit in these sources. So I would say more or less every textbook on general relativity, if it has been written after 1970, say, contain chapters on black holes. I've chosen 4 of those textbooks where I find that they are particularly recommendable in view of black holes. So textbooks, maybe I put this here. Textbooks with chapters on black holes. There is the book by Lewis Ryder. That's a fairly new book on general relativity, which, as I find, has very nice chapters on Schwarzschild black holes and Kerr black holes. It is just called Introduction to General Relativity. That's Cambridge UP 2009, so it's fairly recent. And I think it's as easily written as a book on general relativity can be. Of course, it's not really an easy read, like reading about some less challenging matter, but in comparison to other books on the subject, I think it's comparatively easy readable. Then there's one of my favorites, which is a book by Norbert Straumann. Very well-known Swiss astrophysicist. General Relativity and Gravitation and Astrophysics. So the version which I have on my shelf is from '84. So I write this here. This is Springer, 1984. But actually there are several more recent editions. This also has chapters on Schwarzschild black holes, on Kerr black holes, and in particular on the astrophysical aspects. I think Ryder is more on the mathematical side, on the theoretical side, but Straumann also touches astrophysical aspects to some extent. Then, of course, there is a book which we usually call the Brickstone or the telephone book. This is Miesner-Thorne-Wheeler. Gibson, John Wheeler. So people who are interested in relativity know all these 3 names. John Wheeler was a person who inherited Einstein's chair in Princeton, one of the best-known relativists, the one, in a sense one could say, who founded the relativity school in the United States, at least one of the 2 schools, I should say. The other one was Peter Bergman. Kip Thorne, everyone who has seen the movie Interstellar knows his name, right? Kip Thorne is a person who was a scientific advisor for this movie and who designed these pictures of the black hole, which you saw in this movie. very well-known astrophysicist, and Charlie Meissner is also a very well-known relativist who did very important and very fundamental work on relativity. Actually, when our Graduiertenkolleg, which I just mentioned, was founded, we had Charlie Meissner as a keynote speaker, so we were very happy to have him here in Bremen. So this book is called Gravitation. Appeared with Freeman in 1973. And the authors were so happy with this book that they never wrote a second edition. It was never revised in any way. It is just as it came out in 1973. And of course, so you can imagine in various aspects, in particular in view of observations, of course, it's completely outdated. Yeah? But the theory is forever. Yeah, the mathematics is, if it is true once, it is true forever. So it is still a very useful book, and it's really voluminous. Yeah, as I said, we usually call it the brickstone because it has the shape of a brickstone. Yes.
It's still available for some older books. There's the problem that even if they're still quite actual or quite thorough, they're not available anymore.
Yeah, okay, the question was to what extent these books, and in particular the last one, is available. Actually, I'm not sure if we have it here in the library. I have my own copy, so I never looked for it in the library, but I would guess actually that I have at least 1 or 2 copies.
Yes, one.
Yeah, okay, so it is available here. Okay, and the last one, which I want to mention in this category for the more mathematically oriented, one of my favorites is a book by Bob Wald, who is one of the leading mathematical physicists of our times, I think one could say. The book is called General Relativity. This is Chicago University Press, 1984. And so this is not so much on applications to astrophysics, but it's very precise and very thoroughly written in view of the mathematical theory. So these are textbooks which have extended chapters on black holes, and then there are a few monographs devoted directly to the topic of, to the subject of this course. So let me continue here. So monographs on black holes or related subjects. Maybe the book which I would recommend most for being used in parallel to this course is the one by Frolov and Novikov. These are 2 Russian scientists. Frolov is now in Canada. Igor Novikov has returned to Russia a couple of years ago. And the book is called Black Hole Physics. So it's written in English, not in Russian. And it came out with Kluwer, 1998. It addresses a lot of subjects, more or less everything which is of relevance in view of black hole physics is mentioned in this book. It doesn't go as deep as some of the other books. So if you have read the corresponding chapter in this book, then you would get, I think, a fairly good idea of what this subject is about. And then usually if you are interested in more details, then you would have to look at some other books in addition or some research articles. But the basic way in which things are presented, I think, is very, very recommendable in this book. And then there is, of course, the monograph by Hawking and Ellis. It's not specifically to black holes, but to something where black holes play a very important role. The book is titled The Large-Scale Structure of Space-Time. As many of you know, Stephen Hawking came in second for the Adams Prize in 1965 or something like that. Number one was Penrose, and number two was Hawking. And these Adams Prize lectures, they were the basis for this book. So this book is an extended version of this essay by Hawking. And it's basically on the subject of singularities, not only black hole singularities, but also cosmological singularities. So both things are treated in this book, but in particular, black holes are extensively treated. And as you certainly know, Hawking is one, both of them, Hawking and Ellis, are among the main players in this field. So they made important contributions. This is Cambridge UP 73, yes. Okay. Mathematically challenging, much more difficult to read than this here. Then there's a monograph on the Kerr geometry specifically, which describes a rotating black hole. It is by the American mathematician Barrett O'Neill. Maybe some of you know the textbook by O'Neill on semi-Riemannian geometry, one of the standard textbooks on this subject. He has written a second book, which is entitled The Geometry of Kerr Black Holes. And well, I guess everyone knows what the Schwarzschild metric is. So the Schwarzschild metric describes, among other things, a non-rotating black hole, and the Kerr metric describes a rotating black hole. And this book there's a single book devoted to this subject, so you can already imagine that discussing the Kerr metric is a rather challenging topic, and you can fill a whole book with it. It appeared in '95. Mathematically very carefully, because it's written by a mathematician. The comments on physics are sometimes a little bit funny in this book, actually. Yeah? So you can easily recognize that O'Neill is not a physicist, but the mathematics is very, very good, very perfect. And then there's a book by the famous Nobel Prize winner Chandrasekhar. This is called The Mathematical Theory of Black Holes. I think one should mention it because it is really written by one of the most important persons in the field. And it is very, very useful for researchers working in the field. But actually I have doubt if a student, when hearing about the subject for the first time, if such a student can actually profit from this book. So I found it very difficult to read. Actually, when it came out, '84 or so, I was already in the business, so I immediately jumped onto this book and tried to read it, and I found it absolutely awful. And then I put it away and didn't look at it for a couple of years because I found it's absolutely unreadable. And then later I came back and now I love it. I use it all the time. Yeah? But you need a certain background to really appreciate the quality of this book. So I would say if you just want to hear one course on black holes and are not interested to work in this subject beyond this course, then I would not recommend this. So I would mostly recommend the first one for a second reading. Okay, this was a few remarks on the literature. I will give probably more specific references during the course later for specific subjects. And now I should give you an overview on the contents I'm planning to cover in this course. So I will begin with an introduction. Surprise. This will be mainly on the history of the subject. I will give you a little timeline where important steps were done in view of our understanding of black holes, and also make a few remarks already in this introduction about the situation of the observations. I will come back to this later in more detail. So this will be a short introduction. I will certainly manage to finish this today. And after that, I will do a brief review, very brief review of general relativity, of the formalism. Actually, what I expect is that everybody who is taking this course has encountered general relativity already before. Yeah, so if you see for your first time a Christoffel symbol or a metric tensor, then I would guess it would be difficult for you to follow this lecture. Yeah? You're very welcome. I don't want to, to chase away anybody, but actually it is thought for people who have already taken one course in GR or written a book on GR, so that they are familiar with the basics. So what I want to do here is just refresh our memory on the basic facts on which general relativity is based and introduce my notation. There are conventions which are used differently by different authors, so I have to fix this. So this will also be a very short section. Then I will talk about something which I guess is also to a certain extent familiar to most of you. Namely, I will talk about Schwarzschild black holes. So if you have taken a course on GR, then you have certainly heard about the Schwarzschild metric, and you have heard about the fact that, among other things, the Schwarzschild metric describes black holes. It also describes ordinary stars. It has a field around an ordinary star as long as it is spherically symmetric. Spherically symmetric means, in particular, non-rotating. Yeah? If it's rotating, then it's not spherically symmetric, because the rotation axis distinguishes one direction in space. So the non-rotating, this means the spherically symmetric objects are described by the Schwarzschild metric in GR. Oops. And okay, I will refresh our memory on the Schwarzschild metric, and I will then discuss, with a certain length actually, what the Schwarzschild metric has to do with black holes. So we will repeat the Eddington-Finkelstein coordinates, which are probably familiar to most of you. We will also introduce some other coordinates, which maybe you do not know, namely the Pernier-Gullstrand coordinates and the Lemaitre coordinates, which are associated with infalling matter. Eddington-Finkelstein coordinates are associated with infalling photons, with infalling light rays. They can do the same thing with infalling matters, then you get other coordinate systems. I will study them. I will also study the lensing features of black holes, the multiple imaging properties of Schwarzschild black holes, the shadow of a Schwarzschild black hole. So I think I will address a few subjects which you do not know from your first course in GR. But apart from this, also in this section, there will be a fairly large part which is just a recap of things you have probably heard before. And then we begin with a field which is actually, which I expect that it will be new for most people in the audience. I will speak about the spherically symmetric collapse. This will be in particular the famous Oppenheimer-Snyder paper. So that's the question how a Schwarzschild black hole actually forms. Yes, in the Schwarzschild metric, everything is static. We have no time dependence, so the thing exists for all times. Yeah? It has come into existence at t equal minus infinity, and it exists until t plus infinity. And you don't ask the question how this thing has formed, and this is a question we want to address here. So we consider matter which really collapses, and at some time the horizon is formed, and then it is a black hole. So this will be, mathematically not too challenging. And then comes the time where we have to speak about Kerr black holes. And this will be a very long section, actually. I think I will spend something like 3 weeks on the Kerr metric. As I said, O'Neill has written a whole book on it, so you could easily spend more than 3 weeks. But I think 3 weeks you should spend on it. So that's rotating black holes. Yeah? So the Kerr black hole has two parameters, a mass and a spin. If the spin is 0, then you get the Schwarzschild metric. So this is a special case in this family. But if the spin is non-zero, then you get something with new and interesting features. So then you get something which is called an ergosphere. You can discuss this famous Penrose process by which you can extract energy from a black hole. These are features which a Schwarzschild black hole does not have, so you need a Kerr black hole for this. Then I will discuss some other exact solutions. These are exact solutions to Einstein's vacuum equation in this case. So this is a non-rotating and this is a rotating black hole solution where the central object has no other features than a mass and an angular momentum, a mass and a spin. Could also have a charge, for instance. Yeah? It could also have more funny things. It could be coupled to Young-Mills fields or to scalar fields or whatever. And if you allow for such additional couplings, or it could have a cosmological constant, for instance, then you get more complicated solutions. And I will briefly mention some of them. But I think if you have understood the Schwarzschild and the Kerr, then you have, I think, 95% of what is interesting about black holes you have understood. And the other ones, I think, are more of a speculative nature. But I will mention some of them. Reisner-Nordström, Kotler, maybe also Taubnat. I'm not sure about this. But a few others I will mention. So this, up until here, this will be very much on the mathematical side. Yeah, we will study solutions to Einstein's field equation, discuss the mathematical properties, discuss how particles move in this space-time, or how photons move in this space-time by studying the geodesic equation. Now the question is, what has this to do with our nature? Are there really things up there in the sky who are properly described by these things? And this will be a long section now. Astrophysics of black holes. So I guess most of you know that there's very good evidence by now that black holes actually exist. And this evidence is for two classes of black holes. One are the so-called supermassive black holes. They are supposed to sit in the centers of galaxies, in particular in the center of our own galaxy. And they are called supermassive because they have something like 1 million solar masses, at least. Maybe even 1 billion. Yeah? 10 to the 6 to 10 to the 9 solar masses. That's the typical mass of such a supermassive black hole. And in this section, we will discuss why we are almost completely convinced that these things exist. And then there's a second class where we are also very optimistic that they do exist. These are the so-called stellar black holes, where the mass is not very much more than 1 solar mass. Maybe 10, maybe 15, but not more than that. And there are also good candidates for this. The best known and the oldest known is Cygnus X1, the X-ray source in the constellation Cygnus, which became in the 1970s already a good candidate for a black hole. And until now, the evidence has become even bigger. Maybe you know about this bet by Stephen Hawking and Kip Thorne. Stephen Hawking is famous for offering bets to his colleagues on various subjects. And one of them, I think the first one, was with Kip Thorne about the existence of black holes. And in particular on the question whether Cygnus X1 is a black hole. And Hawking said no, and Thorne said yes. And after a couple of years, Hawking paid up. So he said, okay, I accept now, it is a black hole. And he later said that he never doubted that it is a black hole. He just offered this bet as a kind of insurance because he had spent so much time on working on black holes that he would be awfully disappointed if it would ever come out that they don't exist. So he said, then at least I would have the consolation of having won the bet. So that was the reason, as he said, why he offered this bet. So Cygnus X1 was a subject of this bet. So we will speak about this. So these are the two classes of black holes where we are fairly convinced that they do exist. Then there are two other classes, much more speculative. These are the so-called mini black holes with a mass very, very much less than 1 solar mass. There are speculations that they might have been formed during the early stage of our universe. These are the so-called primordial black holes. They would be in this category. There was fear that they could be formed in the LHC. You have all read this in the newspapers. Apparently they have not formed. But well, there's a certain speculation about this, that they could. And so these are the mini black holes, which we don't know if they exist. And then there's also between the stellar mass black holes and the supermassive black holes, there's something which is called intermediate black holes. Maybe a few hundred solar masses, maybe 1,000 solar masses, something like that. There's speculation that they might form at the center, for instance, of globular clusters. But the evidence for them is not very strong. So they are much more speculative than the stellar ones and the supermassive ones. So we will mainly discuss the stellar ones and the supermassive ones in this section. Okay, and then we have to see how far we are in the term, how much time is left. And then I will fill the rest with mathematics on black hole theorems. There are various mathematical theorems on black holes. And yeah, we have to see how much of them I can discuss here. So you have certainly heard about the singularity theorems, which are associated with the names of Penrose and Hawking. So I will certainly make at least a few remarks on them. Let's see to what extent I can actually go into details. This is also a subject where you can fill a whole course with. Actually, twice in my life I have given courses on the singularity theorems alone. So the whole course was on these theorems. So you can easily fill a whole course with this. And I think I will try to give you some ideas about this. Then there are the so-called no-hair theorems, also known as black hole uniqueness theorems. So these are theorems of the kind that, where the basic one says if a black hole has a mass, an angular momentum, and a charge, no more. So no coupling to Young-Mills fields, for instance, or to scalar fields or something like that. Just a mass, a charge, and an angular momentum. Then the field is uniquely determined. Yeah? Then it is what is called Kerr-Newman, the charge Kerr metric. Yeah? There are no other black holes which are characterized just by these three parameters. So this is a surprising theorem, actually, because if you think of the object having formed during collapse, then in the beginning the object will have many, many more properties. It will have different higher order multipole moments. Yeah, the higher order is a quadrupole moment, octupole moment, and so on. And yeah, it will have many other different properties. All these properties are lost when a black hole is formed. Only these three parameters survive. And there's a famous figurative way of speech in order to express this. One says that black holes do not have hair. Yeah? So all the other properties, they are like the hair a person has, which distinguishes different persons from each other, and all this is lost when a black hole is formed. This, that's the reason why it's called, why it goes under the name of no-hair theorems. And you usually read that this word was invented by John Wheeler, who actually also invented the word black hole. But Wheeler himself said that that's not true. He learned the word from a younger colleague by the name of Jakob Bekenstein, who is the inventor of black hole thermodynamics. So the way of expressing this uniqueness theorem by saying that a black hole doesn't have hair, it actually comes from Bekenstein. And I will certainly address this here in this section. I will also try to say a little bit about the black hole thermodynamics. So you have maybe heard about the fact that that there's a certain analogy between thermodynamics and black hole theory. So in thermodynamics you have something like a temperature. You can introduce a quantity for black holes which has the same mathematical properties. It's the so-called surface gravity. In thermodynamics you have entropy. You can introduce an analogous quantity for black holes. It's the area of the horizon. And then you can formulate statements for black holes which are formally completely analogous to the thermodynamical laws, to the first law, the second law, and there's also a version of the third law. And this was something initiated by Bekenstein and then further extended by Hawking, and I will also address this a little bit. In this connection, also the famous Hawking radiation plays a certain role, because this gives physical meaning to the temperature. So the temperature, which is associated with a black hole in a rather formal way, actually turns out to be visible when a black hole is treated at least partly in a quantum theoretical way. Then it starts radiating. It's no longer time independent. It's no longer existing forever. It starts radiating, and what it radiates is blackbody radiation with precisely this temperature, which you associate with it. I think I can say at least a few words about this. But as a general rule, I am planning not to address quantum theoretical aspects of black hole. So this will be a course on the classical aspects of black holes. I think you can understand Hawking radiation, at least some aspects of Hawking radiation, just in the language of classical physics, and that's what I would like to address here. About quantum black holes, I will not speak. There are two reasons. First, time is too short, and the second reason, which is more important, I don't understand this. I cannot speak about this, because my own knowledge about this subject is much too less for giving a lecture course on this. I hope it's sufficient to give a lecture course on this. This is what I want to do here. So that will be the plan for the course. So the last one is, in a sense, open-end. So when the term has come to an end, then I have to stop. So I don't know what exactly I will do in this section. But this is, so to speak, the program which which I really want to work through, and which I think one should know if one wants to discuss black holes in a technical way, just going beyond popular science, speaking in terms of popular science. Okay, so let's begin with the introduction. And as I usually do, I will order this a little bit in a historical way. So I will write down a few years where important things were done. And I want to begin, well, not with Einstein. Actually, in a sense, the story of black holes began before Einstein. There were at least two people who thought about something which is very close, or at least to some extent close to what we now call a black hole, but they considered this already on the basis of Newtonian physics. And the two gentlemen who did this was the Englishman John Michell in 1783 and the Frenchman Pierre-Simon Laplace. So John Michell, let me write, speculates about objects from which light cannot escape. And I will explain this in a minute, what he meant with this. And a little bit later, 1796, Pierre-Simon Laplace, as a famous French mathematician, everybody knows the Laplace operator and many other things he has done. He even calculated, he explicitly calculated escape velocity for such a dark star, as you might call it. So what was the idea? So this was on the basis of Newtonian physics. Newton himself and many of his contemporaries thought of light as being consisting of particles. As that light is a stream of particles. That was a corpuscular theory of light, which at this time was favored by many scientists. A little bit later, say from the year 1801 onwards, the wave theory of light took over. 1801, this was the year when Young did his famous diffraction experiments, and then the wave theory of light took over. But in the 18th century, the corpuscular theory of light was still very much favored. And the idea was the following: if I have a body, a star for instance, or a planet, something spherically symmetric, then everybody knows it has a mass m and it has a radius r. And if you want to shoot an object vertically upwards so that it actually can escape to infinity, then you need a certain minimum velocity. If you do it with a velocity which is too small, the object will go up and then it will fall down. Yeah, it will reach a certain maximum height and then fall down. And then there's a minimum velocity which is sufficient just to arrive at infinity with a speed equals 0. And if the speed is bigger with which you start, then it will arrive at infinity with a finite speed. And this velocity, which is at the borderline, is called the escape velocity. And you can easily calculate it in terms of Newtonian terms. And now if you have the idea that light consists of corpuscles, particles, and if gravity acts on these particles in the same way as it acts on all other particles, that means that it gives a unique acceleration to these particles, which is determined by the gravitational field, so in this case by the mass of the body. Then you can calculate the escape velocity for light. Yeah? And you see, at this time, it was very well known that the velocity of light is finite. Yeah? The order of magnitude of the speed of light was very well known at this time already. There was a famous observation of the Jupiter moons by Römer, which was before this. So I knew speed of light is something like 300,000 kilometers per second. Maybe not, of course, not with the precision which we know it nowadays, but the order of magnitude was well known. And so what Laplace did was he just calculated what is the relation of radius and mass of this body. So there's an object with the speed of light cannot escape, because the speed of light would then be too small in comparison to the escape velocity. And this is a little calculation which is so nice that I think we should do it on worksheet 1. Yeah. So this will be the first problem we discuss in the tutorials here. And actually the way in which Laplace did it can be found in the book by Hawking and Ellis, which I quoted. In the appendix, there is Laplace original proof given. It's quite funny. If you read it, it's quite amusing how it... Actually, if you do the exercise, I would strongly recommend it to do it by yourself, not to look there. Because with your knowledge from elementary courses, you can do it much quicker than Laplace did it. So he did it in the way of his time, of course. Yeah. And if you look it up, you will see that he has a very funny way of treating differentials. Yeah? So he calculated with his little d's in a way which looks really, really daring for us nowadays. But he arrived at the right result. Okay, so this was, in a sense, you could call this a black hole, right? So if the ratio of the radius to the mass of this body is in such a way that light couldn't escape, and now you are an observer far away, then it couldn't be reached by light from this object, right? So the light would just go up a little bit and then it will fall down, according to Newtonian theory. And if you are far away from it, the light would never reach you. So you couldn't see the star. So in a sense, you could call this a black hole. And the funny thing, by the way, is that the critical radius in terms of the mass is given by something which relativists know very well. This will be the famous Schwarzschild radius. Yeah, the Schwarzschild radius, what we now call the Schwarzschild radius, appears in this calculation. But if you think a little bit, it's not too surprising, because what do you have in the calculation? You have the gravitational constant, you have the speed of light, and you have the mass of the body. And now try to make a radius out of these quantities. The only way in which you can do it is the Schwarzschild radius. So actually it's not too surprising. So what could have been is maybe a factor of 4 or a factor of 8 or something like that, yeah? But more than that actually couldn't happen. So this was early black hole theory, and very easily understandable black hole theory. But that's not what we want to discuss in this course. These are the black holes on the basis of general relativity. And this started, of course, 100 years ago. We are celebrating now 100 years of general relativity. Yeah, Einstein's famous paper where he published the field equation of general relativity was submitted in November 1915. That's what we are celebrating this year, with many events. So Albert Einstein publishes the field equation of general relativity, or Einstein's field equation as it is usually called for short. And then very soon after this, one of the most important solutions to this equation was found. This was done by Karl Schwarzschild. Just a few months later, early in 1916, Schwarzschild found this solution which is named after him. And this will play an important role during the whole course, because among other things, it describes a non-rotating black hole. So he finds a spherically symmetric and I put in brackets and static solution to Einstein's vacuum field equation. So why do I put static in bracket? Well, actually, Schwarzschild assumed that the metric is static, so he really put it into the assumptions. But a few years later, it was shown that this is not necessary, that it comes out automatically. So if you just look at spherically symmetric solutions, you get the same class. You don't get more. There are no ones which are not static. And the fact that these solutions are automatically static, this is known as the Birkhoff theorem, because it was proven by the American mathematician George Birkhoff. So this paper by Schwarzschild has a rather dramatic history. We are in the year 1916. If you have a certain background knowledge in history, you know that there was something important going on in Europe at this time. This was in the middle of First World War I. And actually Schwarzschild was at the front, at the Eastern Front at this time. He was not lying in a trench, he was just working behind the line, doing some paperwork, working as a how do you say in English, meteorologist or something. So people who are predicting the weather, and he was doing some other paperwork, so he was out of immediate danger. Nonetheless, he caught a disease at this time when he was in Russia, which actually killed him very shortly after this. So it was a very dangerous, very painful skin disease. He was just able to return to Germany. He spent a few weeks in the hospital and then he died as a consequence of this skin disease. So this paper, where he established the spherically symmetric vacuum solution, this was written in Russia and he sent it by the field post to Einstein. Einstein presented it to the Academy and was enthusiastic that somebody was actually able to solve his equations exactly. He hadn't thought until this time that it was possible to find any exact solution. He thought one could just do it in terms of linearization, approximation, or things like that. So he was very much impressed by this paper by Schwarzschild. And so that's the reason why it's called the Schwarzschild solution. There's bad luck for another fellow by the name of Droste, who found the same solution just a few weeks afterwards. So some people say one should call it the Schwarzschild-Droste solution because the time difference is so small, but there's no doubt Schwarzschild was quicker, and usually it's called the Schwarzschild solution. So Droste was a PhD student of Hendrik Lorentz, the famous Nobel Prize winner in the Netherlands. And he found this solution as a subject of his PhD thesis, and just a few weeks too late. Incidentally, the way in which we write this metric, I will discuss it, of course, again in detail, although I assume that most of you have seen it before. We usually write it in this coordinate, which we call little r, and we call it the Schwarzschild coordinate. That's how we find the metric in almost all textbooks. Actually, in this way, Schwarzschild never wrote it down. Schwarzschild never used what we now call the Schwarzschild coordinates. Actually, in a sense, he used it during the derivation, but before he wrote down the final result, he made a coordinate transformation to something else. And he made the coordinate transformation in order to push this singularity in quotation marks, which appears at the Schwarzschild radius. Yeah, I think everybody in the audience has heard about this, that this metric has a famous singularity at a particular radius, which was called the Schwarzschild radius. So Schwarzschild himself pushed this into the origin, because he said the singularity outside of the origin is bad. We shouldn't have this. Yeah? In the origin, it's acceptable. We are used this from spherical coordinates. Yeah? So just the coordinates break down at the origin. That's not a problem. But if they are outside, then it is a problem. So that's of course not a way of solving the problem. It's a way of covering it up, right? So he just made it invisible. And the way in which we write the metric nowadays goes back to Hilbert. So Hilbert, very shortly after Schwarzschild, discussed this solution. He wrote it down in the way we nowadays do it, and somewhat confusingly, he calls this coordinate the Schwarzschild coordinate. So many people think that's the way in which it can be found in the original paper, and if you look this paper up, you will think, what the heck is this? This is not the Schwarzschild solution I'm used to. So it's really hidden in this paper. And some people even say one shouldn't call it the Schwarzschild solution unless one pushes a singularity in the center. But I think that's a little bit overdoing it. It's certainly justified to call this a Schwarzschild solution. So we will study this in great detail. Oops. Then very soon after this was generalized by introducing a charge and also by introducing a cosmological constant. That's fairly easy. So with a charge, the one who did this was Hans Reisner, a German engineer. I think he's best known for constructing a kind of airplane, which is called, it's some bird, Reisner duck or Reisner dove or something like that. So this is an airplane, one of these early airplane types. So this was his main business. He was an engineer, an airplane engineer, and for some reason he became interested in relativity and wrote just one paper on relativity. And he found this solution, which is named after him. And a little bit later, another one, a very much better known relativist, namely the Finnish relativist Gunnar Nordström, found the same solution. Actually, Nord Stream was 2 years later, 2 years after Reisner. And in this case, it is usual to call the solution the Reisner-Nordström solution. Yeah? Between Schwarzschild and Droste, there are only a few weeks, and everybody calls it the Schwarzschild solution. Between Reisner and Nordström, there were 2 years, and everybody calls it the Reisner-Nordström solution. Sometimes the community is not fair. And later Nordström found the charged version. Yeah, with an electric charge. The charged version of the Schwarzschild metric. And that's called the Reisner-Nordström solution. And we will also discuss it a little bit. It's probably not too interesting in view of astrophysics because we are fairly convinced that the net charge of an astrophysical body is very, very close to zero. Yeah? That you have stars in the sky, celestial bodies with a net charge which contributes in an essential way to the exterior field is very unlikely, actually. And for this reason, this is more of a mathematical interest. But actually, there are some people who speculate about charged black holes, that they might really exist in the universe. So they cannot be completely ruled out, but most people would say this is very unlikely. And then there was another modification, which was also fairly easily found. This was done by Kottler, Ferdinand Kottler, the Viennese. There was a very successful Viennese school of early relativists around Hans Thirring, and Kottler was one of them, and he found modification of the Schwarzschild solution by a cosmological constant. So here I wrote solution of the vacuum equation, Einstein's vacuum field equation. I meant the vacuum field equation without the cosmological constant. And Kottler did it with the cosmological constant of the Schwarzschild solution. With a cosmological constant. So I think one should call this a Kottler solution. You find it under this name frequently, but you also find the name Schwarzschild-de Sitter solution. The reason is that it combines two other solutions, namely the Schwarzschild and the de Sitter solution, into one solution. But neither Schwarzschild nor de Sitter ever wrote down this solution. So that's the reason why I think one should call it the Kottler solution. Okay, and then for many, many years, actually, nothing really important happened. So the Schwarzschild solution was around, and also some modified solution. And there was this strange singularity, in quotation marks at least, at a certain radius value. And people thought about what could be the reason for this. In particular, Einstein addressed this subject several times. He never understood during his lifetime what was going on at R equal RS. He never understood it. And he died in 1955, and it was understood only after his death, in the late 50s. Then it was understood. What you learn nowadays in the GR course, that there is a horizon. Yeah? He was just puzzled by this thing. He wrote one paper where he tried to explain it, but they don't put it down because it's really a strange paper. It was in the mid-30s. He considered what is now called the Einstein cluster. It is a star cluster where, don't ask me why, stars are only allowed to move on circles. Yeah? They are only allowed to move on circles on the center. And then Einstein found that this is not possible beyond R equal RS, which is of course true. We know this. Yeah? And he said, oh, then the stars cannot reach R equal RS and there's no problem. This is a very funny argument, yeah? Because why should stars be allowed only to move on circles? Yeah? I could take a star and just drop it radially into the center, and then it would encounter this radius value. So on other aspects, the paper is quite interesting, but this argument that he tries to do away with the singularity with this argument, this is really, really strange. And of course, nobody took this seriously. And so the explanation of what was going on at R equal RS, and this was an understanding towards what we now call a black hole, this was only in the late 50s. And in this long period, let's say from Schwarzschild to the understanding of what was going on at R equal RS in the late 50s, I think there was only one paper which made an important and positive contribution to the subject. This was the one by Oppenheimer and Snyder, who calculated the radial collapse. This was 39? In the 30s at least. Where am I? Yes, 39. So this was Robert Oppenheimer, J. Robert Oppenheimer. I think everybody knows his name. He was a leading scientist in the Manhattan Project, yeah, the American atom bomb. He wrote a couple of papers on GR, actually. He mainly worked on quantum theory, but he also wrote a couple of papers on GR. And together with a PhD student, I think it was a PhD student by the name of Snyder, he calculated the gravitational collapse. Oops. Of a dust cloud. Did I write spherically symmetric? No, of a spherically symmetric. That's important. Dust cloud. So, what you consider is you have a ball, and that's a very simple model of a star. Namely, the star is supposed to have no pressure. That's what we call a dust. Yeah? It's a perfect fluid without a pressure. So what will happen if you have such a thing and now you let it go? Of course, it will collapse under its own gravity. Yeah, and that's what they calculated. And well, if it has a finite radius, then everything will collapse within a finite time. And then a singularity is formed at the center. Yeah, so the density becomes infinite at the center. Actually, you ask yourself what else should happen. Yeah? The thing is spherically symmetric, so the collapse is in the radial way, and where should the particles end up if not at the center? Yeah? They cannot do anything else. So actually you are not very much surprised by the fact that here a singularity is formed. But nonetheless, it was the first explicit calculation of a collapse. Yeah? We can really calculate the way in which a star collapses to a thing which we now call a black hole. And for this reason, I think it's a very important paper in this field, and we will discuss this calculation in this course. Just to jump a little bit ahead, then in the 60s there came the singularity theorems, and they generalized this result in a very surprising way. So here you would say, if you read this, you say, well, I had expected this result. Yeah, singularity is formed because of the symmetry. Yeah? What else should happen? But what Penrose and Hawking showed is that the formation of a singularity is generic. It has nothing to do with symmetry. If you do it without the symmetry, if the thing is not spherically symmetric, if it is deformed in a way, on a very generic condition, a singularity will form all the same. And that's very surprising. And that's the subject of the singularity theorems. So this is, in a way, this is a preliminary study to understand the singularity theorems. So that's the very first and by far the simplest situation to which these theorems apply. So as I said, I would say this is the only important contribution in this long period between Schwarzschild and Finkelstein, who explains the nature of the horizon. Which was something like 40 years, right? In this period, why was Oppenheimer interested in this problem? At about the same time, he had calculated the final state of stars. Well, as you probably know, there are two known final possible states of stars. One is called a white dwarf, and the other one is called a neutron star. The white dwarf case was treated by Chandrasekhar in 1934, I think. This won him the Nobel Prize. Yeah, so he found out that if a star collapses, it's possible that it ends up as a white dwarf. Yeah? So if the gravity supersedes the outward pressure, the thing would collapse, and there's a stable end state, which is called a white dwarf. But, and that was a crucial thing Chandrasekhar found, this only works if the mass of the thing is less than 1.3 something solar masses. If it's heavier than this, then it cannot be a white dwarf. The thing cannot be stable. It would collapse further. And we know very well that there are stars up there which have heavier, which are bigger masses than 1.3 solar masses. So what happens to them? There are two possibilities. Either they blow up a considerable portion of their mass, they blow it away, so that then they could collapse to a white dwarf, or they go through the stadium of a white dwarf and collapse further. And then the question, what happened to them? There's a second possibility, they could end up as a neutron star. And this was what Oppenheimer calculated at about the same time, also 38, 39 or so. And he found that a neutron star could also be a stable final state. And he actually found a maximum mass for this of something like 0.7 solar masses. But this had been modified later, so we now believe that neutron stars can exist up to 2, 3 solar masses, something like that. So 3 solar masses is probably possible, but not much more than that. So again, we have a finite mass, a limiting mass. And this calculation was at least partly motivated by the question what could happen to something which cannot end up as a white dwarf or as a neutron star. And nowadays we know it can end up as a black hole. And this is the simplest way, the easiest model, the most idealized model in which a black hole can be formed. And in this context, it was a very important and very interesting paper. Okay, now we are in the 50s, and now we are finally at the stage where we understand what happens at the horizon, as we nowadays call it, in the Schwarzschild solution. And the person who published this result first was David Finkelstein in 1958. He explains the singularity. I put this in quotation marks because, as you probably know, it's a singularity only in a very mild way. It's a so-called coordinate singularity in the Schwarzschild solution. At this radius, which we call the Schwarzschild radius, R equal Rs, as well in his terminology, as a one-way membrane. That's the way he uses in this paper. That's what we now more commonly call a horizon. That's something which can be crossed in one direction, but not in the other direction. And this was the explanation, what's actually going on at R equal Rs, why it is important, but it's not important in the sense that some physical quantity becomes singular there. Nothing of this sort. So locally, by local experiments, you cannot distinguish the area near R equal Rs from any other area. And well, I said Finkelstein was the first to publish this. There's still a debate who actually found this out, who was the first to find this out, because there were other people involved whose results were later published, but maybe they got it first. So there was also some other names which are involved with this, was Sekeres, Hungarian mathematician. Then there was Kruskal, American physicist. And there was a Norwegian called Frønsdal. All of them published papers on more or less the same subject with more or less the same result. And I think all of them understood very well what was going on at R equal Rs. But Finkelstein's paper was published first. And in this paper, he used what is called now Eddington-Finkelstein coordinates. Yeah? I think most of you are familiar with this. Actually, he rediscovered these coordinates. They were used by Eddington already in the 1920s. But Eddington, can you not read this? Yeah, my handwriting is always a problem. This is Sekeres, S-Z-E-K-E-R-E-S, Kruskal, and this is Frønsdal. I think the Norwegians, they have this O with a slash through it. I think he's still alive. Finkelstein is still alive, of course. Yes, I met him a couple of times. He's a very funny person. I once attended a celebration where a new institute was founded, and everything was very, very solemn and very, very decent. So there was a pianist who played Chopin, and she came in a long evening robe, and there were flowers on the stage. And then Finkelstein gave the keynote speech, and he appeared in a jogging suit. The speech was excellent, by the way, but his appearance was a little bit strange. So he's a very, very funny and very friendly person. And I think Frønsdal is also alive. Sekeres and Kruskal, they have died a couple of years ago. Okay, and of course we will discuss this, what the subject of the Finkelstein paper again. So we will really try to understand what's going on at the Schwarzschild horizon. So the word black hole actually didn't exist at this time. So you sometimes found in the literature the word frozen star. I think in particular in the Russian literature this word was used for some time. The word black hole was introduced only in the 60s by Wheeler. So it comes a little bit later in this timeline. And the word horizon, actually, it is not used in the Finkelstein paper, but it was around already. It was introduced by my teacher Wolfgang Rindler in his PhD thesis, but in a cosmological context in '56. Yeah? So the event horizon and the particle horizon is something which occurs in cosmology. This was in Wolfgang Rindler's PhD thesis. Probably Finkelstein didn't know this. At least he didn't use this word. But soon after this paper, people started calling this an event horizon. I think that's a good way of putting it. Okay, I should hurry up a little bit. Where are we now? We are now in the late 50s. And well, in the 60s, then the field became really vibrant. And sometimes I think I would really have liked to live in the 1960s, doing relativities in the 1960s. This was the golden era, right? Otherwise, I would be even older than I am if I had lived already in the 1960s. But in this time, there was when Penrose entered the stage, and Hawking and Ted Newman and all these people, when they did their important work. I would really have loved to live at this time, but nowadays, nowadays doing relativity is much more difficult than it was at this time, because all the things which could be done, without much technical effort, where you need big computers or have to do computer algebra in a complicated way, you could really do the relevant things by hand. So this was the golden era in the 1960s. And one of the most important steps in this era was 1963, the discovery by Roy Kerr, a mathematician from New Zealand. He found the rotating version of the Schwarzschild metric. Yeah, so Schwarzschild was 16, so up to 63. So the step from a non-rotating black hole to a rotating black hole took quite some time, yeah. And the metric is much, much more complicated. So he found the solution to Einstein's vacuum field equation. Describing a rotating black hole. That's modern day's terminology. He didn't use the word black hole, of course. Vacuum field equation describing a rotating black hole. And we will discuss the Kerr solution in quite some detail. Any one of you interested in bridge? Anyone playing bridge? Then, if you would be interested in bridge, you would certainly know the name of Roy Kerr, because he's a famous bridge player. He was in the national team of New Zealand, the national bridge team, for quite some time. I have no idea about the rules of bridge, so I cannot comment on this. Yeah, as I said, this was the golden era, so there were a couple of other important things. 1963 to, say, 69. This was a time when Penrose and Hawking formulated their singularity theorems.
Mr. Pence?
Yeah?
I found the Kerr paper and it was just 2 pages.
Right.
How could you understand this solution just from those 2 pages?
You cannot. Okay, the remark was that this paper by Roy Kerr, where he presented the solution, is only 2 pages. And the question was, how could you understand the metric from this paper? And my answer is, you cannot. Actually, this paper is, maybe I shouldn't put it this way, but you could get the impression that the idea was just to claim ownership without giving away too much information. I think that's the way in which the paper is written. It's very, very difficult to read. And many people then, when this paper appeared actually, there was a conference organized by Roger Penrose, devoted especially to this metric, where the best experts of the time started to explain the properties of this metric, and it took them busy for several days, as one can imagine. So from this paper alone, you understand very little, and as I said, you can write whole books about just this metric. So we will try to understand some basic features of this metric later. As I said, I'm planning to discuss the Kerr metric in quite some detail. So then Penrose, who at this time was then one of the main players in the field, and Stephen Hawking. I think everybody knows this name. They formulated their so-called singularity theorems. There are basically three theorems. The first one is by Penrose alone, the second one is by Hawking alone, and the third one is by both of them together. And if there is time enough, I think I will prove the Penrose singularity theorem. So I think this might be possible to go through this. So the statement of this is, as I said already, is that in a certain way, singularities in general relativity are generic. They are not the exception. Yeah? As you might think from this symmetric situation. Yeah? You might think as soon as you perturb the symmetry a little bit, there will be no longer a singularity. No, it has nothing to do with symmetry. That was the upshot from these theorems. And we will discuss this at least a little bit. That's a problem, of course, of general relativity. Yeah? So people say, well, if there's a singularity, I'm not talking about true singularities, not coordinate singularities. Yeah? The singularity in the center of the Schwarzschild solution, for instance, where the curvature becomes infinite. What does this mean? Curvature becomes infinite. It means that the tidal forces become infinite, right? So if you come close to the center of the Schwarzschild metric, you will be torn apart. And in a way that in the mathematical description, this tidal force is even infinite. And infinities, these two sort of infinities are really bad in a theory, right? And where the standard answer is, here we come to the limits of this classical theory. It's not a quantum theory, what we are doing here. It's classical general relativity. And in order to understand what's going on near this singularity, we need a quantum theory of gravity. As long as we don't have it, we don't really know what's going on near the singularity. Okay, so the singularity theorems will be addressed to a certain extent. Yeah, because I had mentioned Reisner-Nordström, I should also mention Kerr-Newman. So Reisner-Nordström was a charged version of Schwarzschild. There's also a charged version of Kerr. This was found by Ted Newman and his collaborators. Actually, Newman also played an important role on the way towards the Kerr solution. So he made important steps towards finding the Kerr solution. Kerr actually found it, so it's okay that it's called after Kerr, but Penrose was quite nonsense. Newman was strongly involved in preliminary work towards it. So, and he found the charged version. So this is, so in the official papers, his first name is Ezra, but everybody calls him Ted. So this is Ted Newman, Ezra Newman and collaborators. Find the charged version. So then you have not vacuum in the outside, you have electrovacuum. You have vacuum and an electromagnetic field. And collaborators find the charged Kerr solution. Charged Kerr solution. If you look at this paper, it's considerably longer than the Kerr paper, and it has much more authors. It has, I think, 7 authors. And the history of this paper is quite funny. At this time, Ted Newman gave a course a course on advanced gravity, advanced GR, and he had 6 students in the class. And as in the exercise classes, he gave them as a problems to check all the details on this solution. And they did it. They even found mistakes. Yeah, so they really contributed to the work. And then Newman decided to put all of them on the paper. So you must just be lucky to be in the right course, and you can have your name on a famous paper. So I will briefly mention the charge version. As I said, we believe that celestial bodies are not charged in a really measurable or important way. So we usually think that the charge is negligible. So the Kerr-Newman metric is certainly not as important as a Kerr metric. What do I have next on my list? Yeah, Wheeler, the word black hole. This was in 1967. John Wheeler gave a talk, I think in New York, not quite sure. In the US, in any case. John Wheeler used the word black hole in a talk. And this caught on then very quickly. Then a few years later, everybody used this word. So the earlier word frozen stars or a collapsing star or something like that, they died out then. And everybody uses it, calls it a black hole. If you are interested in at least the title page, the talk was then published in written form. If you're interested at least in the title page, you find it in the book by Frolov and Novikov. So I have a photocopy of the title page, even with annotations by Wheeler, where you can see that in the introduction the word black hole occurs. So this is so from then onwards the word was in the game. 67 was also the start of the no-hair theorems, which I had already mentioned. The first version was this was for non-rotating black holes, which is fairly simple. This was by Werner Israel, the German-born relativist Werner Israel, who now lives in Canada. So he and others, they proved the black hole theorems, the no-hair theorems, and the final step to prove the theorem in the most general form, in which it is now known, was by Pavel Mazur in '84. So this was a proof of black hole no-hair theorems. Yeah, so these are statements of the kind: if a black hole if it interacts only via gravitation and via electromagnetism, so it has it doesn't interact, for instance, with the Young-Mills field or with a scalar field or something like that. That is completely characterized by the three parameters: mass, spin, and charge. Yeah? So there are not different black holes with the same values of these three parameters. Yeah? So the outside of the black hole is completely determined by these three parameters, and then, of course, it's described by this Kerr-Newman metric, the charge version of the Kerr metric. If the charge is 0, then it's a Kerr metric. So that's also very, very surprising and very important theorem. So in a sense, black holes are much, much simpler than, for instance, neutron stars. Neutron stars are awfully complicated. Yeah, the inner structure plays a very, very big role for the properties of neutron stars. And there's a lot of speculations how exactly neutron stars look in their central part. More or less in every talk on neutron star, you see a picture where you have a cross-section through a neutron stars, and you have a crust, and then the speaker will tell you something about the crust. He has some ideas about it. And then there comes the next shell. He also has a certain idea about this. And then in the center, usually you have something with a question mark in it. And then the speaker will say, we have no idea what's going on in the center. So that's the situation with neutron stars. Yeah? With black holes, it's much simpler. If you knew these three parameters, then we know the whole thing. We know what it is. Yeah? So black holes are much simpler than neutron stars. And we will try to understand how the black holes are characterized. In which way the black holes are characterized by these three parameters. So I think I have only one more. Yes, 69. That's the cosmic censorship. I think I can squeeze this here. Penrose formulates something. So the no-hair statement was in the beginning also a conjecture. So if you look at papers from the 70s or so they spoke about the no-hair conjecture. And then by '84, actually it was proven. And from this date onward, it was a no-hair theorem. Here, in this situation, Penrose formulated a conjecture, but this conjecture hasn't been proven until now, so it's still a conjecture. Sometimes later, maybe it will be a theorem. Roger Penrose formulates what he calls the cosmic censorship conjecture. So what is this? You think of the Schwarzschild black hole. I think everybody knows the Schwarzschild black hole has two interesting features. One is the singularity at the center, and the other one is the horizon. So the singularity is hidden for an outside observer by a horizon. That's what we call a black hole. From the outside, you cannot look inside. Yeah, you cannot get any information from the inside. So there is a singularity, which is bad, but it's hidden for an outside observer. It's forbidden for an outside observer to see the singularity. That's what Penrose called censorship. Yeah? So nature acts like a censor who forbids for outside observers to see singularities at the center. Mathematically, you could construct something which is called a naked singularity. There's a singularity, but no horizon around it. Then the observer far away could see the singularity. Yeah? He could get signals from close to the singularity. And Penrose said, that's really bad. Yeah? And we should exclude this. And the cosmic censorship conjecture says, under reasonable assumptions on the initial state, and now the debate starts, what do you mean by reasonable assumption? Yeah? Under reasonable assumptions on the initial state, naked singularities will not form. And people have tried to prove theorems to this effect. Some preliminary steps have been made, but a satisfactory version of what you could call a cosmic censorship theorem does not exist. But maybe we can discuss a little bit the status of this. So these are three groups of mathematical theorems around cosmic censorship, around the no-hair statement, and around the existence of singularities, which I'm planning to address in the last part of this lecture. And then the fourth group is centered around work which was done by Bekenstein and Hawking, which began in the year 1973 with a paper by Bekenstein, and which goes under the name black hole thermodynamics. So I will try to give you a certain feeling of what we mean by temperature of a black hole and entropy of a black hole. And in this context, I think I will also talk a little bit about Hawking radiation. So they formulated the thermodynamics of black hole. So these are the four groups of mathematical. So these are also mathematical theorems. Here, these laws, which are analogous to the thermodynamical laws, they are mathematical theorems about black holes. So they are, in this sense, they have the same status as the other groups of theorems I've been talking about. So this gives you a brief overview of the historical development of the things we will discuss in this lecture. I will then, at the beginning of the next lecture at Tuesday, I will make a few remarks about the status of observation, and then we start with a mathematical formalism with a recap of general relativity. Okay, have a nice weekend.